have their own accent. And I was talking about even dialects, right? So that is also adding for a particular language, there are so many dialects again. So it's not very easy, but it's not that like it's not doable. So task specific. And yeah, as a, this task specific isolated one. Depending upon the task. So if you are only building a robot, which is okay to accept only a single command, then the vocabulary meant for it is very less. But if you are building an ASR system for understanding the conversation, so then that vocabulary is huge. So there are so many constraints on that. Okay, so this is yeah. So this is the model. You can have it in your mind afresh. This is what is happening inside an ASR system. So we give a speech waveform. Okay, so a waveform is given. Acoustic analysis is done. So in this acoustic analysis, so we can think of something like you give. Pardon me for this bad diagram. So you give a signal, speech input signal. So what this acoustic analysis does is that like it chops the speech signal at a fixed uh, rate, maybe from 10 to 25 milliseconds. Okay, so you just chop them into discrete signals. So this continuous signals is converted into discrete signal. So this we call it as a frame, speaker frame. So this is actually important for us. Okay, so but we do not know what is in there. So this is converted as a feature. So using MFCC spectrum features. So we call it as a, okay. So MFCC is one kind of feature, but you can use any other feature as well. So these coefficients, the spectral coefficient is nothing but it converts into some real value. So it is a vector. So this is a frame. I'm sorry about this blurred image. So this is a frame 1, 2, 3, 4 in each and every frame. So what is the vector? So it is a vector we are trying to understand. So what has been uttered. So this MFCC coefficients are nothing but like how they are designed is that like the way we try to, our ears are able to understand the speech. No? So I'm speaking, so how it is felt by the ears. So it is inspired. So these coefficients are inspired by that. So that's how they get. And the acoustic model tries to understand this. So you have like what is in there in that 25 milliseconds frame. So that's what we get. So we get the acoustic model, and this pronunciation model. This is one part of it. Okay. So we've got some acoustics, some bits and pieces we've got. But what are those bits and pieces? So we have a pronunciation model. So what is pronunciation? A pronunciation model says is that like how a word is pronounced. So that is a different. So that is a different part happening altogether in a different place. So this is given by the language experts. The language experts tell that like good is supposed to be pronounced this way. Phonological representation they will get. So this is matched with this, and we will predict the words. Okay. And one more guy is here, so that is language model. The language model, so what it is helping is that like it is nothing to do with the speech. So language models are nothing but the model that helps to predict the next words. So you would have seen in Google, no? So you type some queries, so some other words predict. So language model is supposed to predict the next word. So because it knows the language. So that is also if something wrong happens, so this will sort it out. If something happens wrong here, so if some word is not predicted correctly, then this language model will predict the correct next word. So because it is based on text. So many deep learning algorithms are, you can visualize each and every process, many deep learning algorithms running at the back end. And that's how all put together. So we get this. So somebody spoke this and we just chopped it into the in on a specific time frame, and we extracted the coefficients of it, and we build this acoustic model, and then we use the pronoun model to guess what has been spoken. And if this was wrong, and we are cross checking with the um, language model. So what a word is given, sequence of word is given, and what is the next. So that is how it's actually done. So this is what happens in a ASR system. So no matter it is a traditional system. So traditionally we were using hidden Markov models, and then we moved on to deep learning models, and today we are using pre-trained models. So like we use pre-trained models for text, and we use pre-trained models developed by Google. So we will also see hands-on, we'll see a code on that, like wave to vec models have been used. So when you see this, the whole process, so what we have to imagine is that a speech is a sequential input. The speech is a sequential input. So it's basically predictions. So when I utter this, so when we speak a word, there are so many sequences involved, right? But our job is to, at each and every point of time, it may be a prediction of this next phoneme that is different, or next words that is different. So next word is done by language model. So next phoneme, so we are doing it here or here. But what we have to imagine is that, like, we are predicting a sequence. So what happens now? So that is predictable. Why? Because speech itself is a sequential thing. No, so a language itself is a sequence thing, right? So we cannot change the sequence. So I ate apple. So you cannot change the. Of course, Indian languages are free word order. So if you just translate the sentence into Indian languages, you can change the verb and the subject. So, but that is not possible with English. So when you are doing it for a Indian language, so then the problem is even more different. So, but the language models are today's language model, the state of the art language models are able to tackle all those. So, what I'm trying to tell is that, like, if at all I've confused for the past few minutes, but it is a speech is a sequence. Maybe it is a word level or a character level. It's a sequence. What we are supposed to do is that, like, we have to think like a finite state automata. So we are in a particular state and we are predicting the next state. So what is next? And then we are predicting and we are validating. That's what is happening. So the summary of the story is that we are predicting a sequence and we are evaluating the sequence, validating the sequence if we are right or wrong. So you're free to ask me any questions. You can. So far, are you all listening? Yes. Fine. Okay, yeah. So this is the first part of it. So the next slide I was showing is the first part of it. You give the speech input. So you're generating the discrete samples. So this is a frame, right? So this table was actually here. So sorry. So this is blurred. Okay. So you are chopping it. I told you, right? Like, this is a discrete signal. So 25 milliseconds or 10 milliseconds, or whatever feels right for that particular data. So normally it is between 10 to 25 milliseconds. This is a frame. And what is in the frame? Each and every frame we are converting into a vector. So this is a vector. So you can think of some number. So these features are nothing, extracted using MFCC. That's what I said. So they extract some features and encode it. That's what is happening. Okay. So then what is the acoustic information? Acoustic information is that we are converting. So this is how it is actually. The prediction is that, like, we are trying to, this is the pronunciation model. Okay. So there's a connect between, if you're able to tap this, then it is. So There's a pronunciation model. There's an acoustic feature. So acoustic feature is actually what it is doing. It is chopping from 25 milliseconds, and it is understanding what is in that particular frame. But pronunciation model is the reverse way. It is already built. It knows that for this pronunciation, this is the word. So it is given by the expert. Okay. But what we are trying to understand is that we chopped those 25 milliseconds frame, right? We are trying to understand whether these kind of pronunciations are there in that 25 seconds. So that is where this guy and this guy gets hand to hand. Okay. So this gives the chopped discrete frequencies, and this will give all together, put together. This will check whether all put together, if you are able to find the words. So that's what I think I made clear. If not, you can ask me. That's what is happening here. So five, this is a pronunciation model will give us the five. It's actually a string of, so this is a string of phones. So this is the phones, and this is how it will be inside the acoustic vector. Okay, one second. My screen is okay. All right. Okay. So why not use the words as the basic unit? Yeah. So many can have this question. So instead of just breaking them into this pieces, right? Why people are not using the words directly? So why are we breaking our head? There's some question in the chat box. Yeah. Okay. Thank you. Okay. So why are we actually using breaking them, and we are understanding tiny? But when we speak of text processing, right, we don't actually do that. We don't go to a character level at all. So you understand the sentence, you understand the paragraph. It's okay to understand directly to the words. We don't go. Of course, character level understanding is done. Maybe when we build a spell checker or something like that, we will go for a character level understanding. But normally we don't go, because the high level text understanding systems, we just stop with the word sentences. We put together the words and we understand like how these words are, when we speak of idioms, right? Like the old man kicked the bucket. So what is the actual meaning, or is it an idiom? It is referring to some other things. We don't bother. So we just understand it as a sentence, or we just understand the words and put together we will interpret. But why are we actually breaking the units into 25 milliseconds, and we are doing this minute thing? Okay. So actually today's scenario we're not doing, but why did they do it at that point of time? Why? Because, so five, for instance, 5 is pronounced as this. Okay. 4 is pronounced as this. This is a string of phones. Okay. 1 is pronounced as this. Okay. So and you have a 9. It was not in the training set, but you have to predict the 9. Okay. So how do you do this? So you can't predict. I mean, there was no a 9 in the training set, but you got a 9 to be predicted in the test set. Somebody is uttering 9. So how do you? So when you were working at a word level, so it will be difficult to predict this 9. But when you break this 9 into phonemes, then this pronunciation will, this combination, the 5. So this AY, no, so it has come here. So somehow this subsets would have got covered in the rest of the training set. So even though you do not know 9, but you can somehow, the probabilistic model, you can predict that this 9 is actually 9. Okay, so hope I made it clear. If I'm not, please do let me know. Okay, yeah, so this is how the mapping from acoustic features to phonemes. So this is a vector, I said. So this frame 1, this is a vector. So vector, I'm telling about a vector, right? So Vector is nothing but like it is, we don't see it as a single dimension. So whether it is a word or a spoken word or a spoken written text, we don't, we call them as an embedding. Okay, so we don't try to only understand them. We try to understand the semantic interpretation of a particular thing. So that's why we see them as a vector. So you see this vector, this actually this. Okay. So, this is the whole dimension of this n. Okay. So how do we actually see is that, like in the earlier days, they were using hidden Markov models. So hidden Markov models are inspired from final state automata machines and Markov property. You know what is a Markov property, no? So it's a probability. So we are in one state and we are transiting to the another state. But what is the probability that I will transit from the state n to n ay? So 9. So 9 1. I think it's 9 1, right? So 9 1. So what is the probability that after this n, this a y will come? So why didn't this w did not come? It won't come because most of the times this w was not coming after n. So there is a probability going on because we are dealing with a sequential input. That's why I said it is a sequence. So when you look at all the probability, all the combos of all the pronunciation of all the words, then they'll all narrow down to a particular probability. So that's what we are looking at. So what is the probability that I will transit from one state to another? That also I will, that is a transition probability, and observation probability is nothing but I'm talking about the various probabilities these hidden Markov models are playing around. So what is the probability that I will predict this n after this ay? So you're predicting something. So if it is already there, you tap the usage. If it is not there, you're predicting. Okay, so this 9 was not there, but you have the bits and pieces of it, and you'll somehow understand, okay, so this is the pronunciation. So that is happening based on the probabilistic analysis. So these probability, this mountains are nothing but the Gaussian distribution. So these probabilities are obtained from the Gaussian distribution. So you don't need to think or worry too much about it. So we can just understand that these acoustic features, these acoustic model is a probabilistic model, and we are trying to interpret. All we need to do is that our job is what? Speech to text, right? Speech to text. So we have to encode speech to word. That is our job right now. So we are somehow trying to predict a word out of this, though we have training data or we may not have. So that's what. So that is a sequence. That's what I'm trying to tell. Okay, so this was a hidden Markov model, so which is playing around with the sequential probability. But now later, after hidden Markov models, deep neural network came. Okay, so their deep neural network also play around with probability only. So you give a speech vector. So the similar way, they come in a compact form, right? So they also predict the observation. So what is the observation? So RNN were famously used for predicting the sequence. So because RNN is a sequential, so because for text and speech we normally use RNN, why? Because they are their structure is different. So this is how they will look like. So input, output, or you can have multiple inputs and single input, or you can have a single input and you can have a output at the end. Okay. So the input is given and it is fed here, and you sequentially process it. So that's why we normally take RNN and we don't have go for a normal ANN. Okay. So deep neural network also did the same job. Okay, so pronunciation model, I'm just again trying to tell. So pronunciation model provides a link between the subword units and the word. So we chopped it and we discovered the subunits of it. And then we somehow, this dictionary was given by the expert, um, and you can come up with a word. Okay. And when we are talking about probability, we are talking about prediction. There are so many uncertainties involved. Okay, so you have five, and this is there, right? So the pronunciation model. So you have a word and you have a pronunciation. Then it's not one pronunciation. So you tell five in a different way, and I tell five in a different way. So some insist on this F, some do not. Or some insist on this V, some do not. So actually, even in pronunciation model, there are so much of uncertainties. For a single word, there's no one pronunciation. Though the dictionary given by the expert is only mapped with the standard pronunciation, so it does not go like that. You have a lot of variation. So this actual pronunciation, if we look at it, for probably, this is what the dictionary will have. Okay, but see the variations of this probably, many have actually spoken in a different way. So there's a probability. So again, you need to have that's why this model came. Okay, so if it is only dictionary mapping, then there is no word called model. What model will do? Model will predict. So it'll learn, it knows the standard form. So this is what probably will have the phonemes structure for this word, probably, but not all the people will speak. This is how we are actually accommodating all the variations of the speakers, and it will only predict. No matter you told this will predict as this. So you should have a probabilistic model, you should have, or you should have a neural network running at the back of this pronunciation model. And yeah, so um, so this is one part of research. Not everybody do, and I have to tell you this. All these slides, this what to say? Yeah, I just got from Microsoft Research. This slides were got from Microsoft Research. So this is the disclaimer I'm putting. So in that slide, so this articulatory feature-based pronunciation was one kind of research attempted. It is not always done. So normally what we do is that we take the word and we try to understand the phoneme. Instead, one part of people, what they did was, so there are so many placements. Okay, so I'm not an expert in this, but I'm just telling you. So these placements, these are the placements when we speak about a particular word. So what they did was 1, 2, 3, 4, 5, 6, 7. Yeah, 7, right? Correct. So they just classified the 7 places. Okay. So how whatever we speak, these places are getting the attention. So the values are predicted based upon the placement of this, where we are actually stressing. So based on that, that is articulatory pronunciation model. So a few people came up. So this is one part of looking at like how to predict the pronounced word. So that's what we are. So any feature we can accommodate. This is one part of it. So I just yeah. So you look at it. So they are so these are the features, no? So labial, dental. I think labial is tongue. I do not know. Dental means it comes from the teeth. I'm able to understand this. Okay, so these are the values they are giving. So whatever you predict, they are given some values. Based on these values, then some prediction is given. So instead of going for phonemes, so few people looked the pronunciation model from this dimension as well. Okay, so this is again the extension of it. Okay, so now what have we done so far is that, just check the time. Yeah, okay, fine. So what have we done so far is that a speech input is given, and then we took the frames and we looked in what is in there, the subunits, and these subunits, we just checked it with the pronunciation model, and then we predicted the words. Okay. But what is our final goal? Our final goal, now it is only the words. But what is our final goal? Final goal is nothing but the utterance, the whole utterance. Let's say we're not bothered about like building an ASR for a single word. We are bothered about building the ASR for a whole a bigger length sentence. Then the pronunciation model and the acoustic model are constrained or restricted to only understand that particular word. They are not brilliant beyond that. But we should have a brilliant guy, more brilliant guy who can help us in understanding the whole sentence, right? So that guy is nothing but this language model. So if you look at the first diagram, yeah. So this pronunciation model and acoustic model, we predicted the words. But this language model guy is going to tell us like what was the actual. So you get a piece of words, okay? So here, I'm so sorry, this Zoom thing preventing to look at my screen. Okay, so good prose is like a window pane. Okay, this was the predicted speech. This is the predicted text. Okay, so let's say this was predicted, this pronunciation word was right, and this was done, and this was done, and maybe this the user did not speak, or the system, the pronunciation models were not so efficient to understand what is this. So till then we only got this good prose like window pane. Okay, so I've deliberately wantedly missed this is and okay, I'm not writing this. Let's say the pronunciation model or the acoustic model um, left it. I mean, we're not able to give, so they gave only these words, but we do not want this. We will not so when you're trying to search the Google, so you'll not be very happy if a broken speech to text is happening, right? We want things to happen in a perfect way. So that thing is actually done by the language model. So we'll just look at like what is a language model. Yeah. So statistical language model. So how likely it is for different words to occur given the recent word context. For example, the dog. So this is what the language model does two type of jobs primarily. It will predict the next word. Okay. So given a set of words or a single word, it will predict the next word. So here it is two words, but no matter like whatever the length of the words, the sentence, it will predict the next word. So that's what we are doing in the Google search, right? And the primary thing about the language model is that what it is actually checking, it just sees the dog run, the dog can, the dog pan. It is seeing all the things and it is calculating the probability inside. It is bothered about like whether I'm in the sense like the system is able to produce a perfect language for that. The model is able to predict for that language. It's language specific. Okay, so if you're building a language model for English, then it should be able to tell like the dog will normally can or normally ran. Okay, the dog will normally ran will be the thing. No? So that makes more sense than the rest of it. So it's again the probability. So that's what I was telling from the beginning. So when you look at it like the human spoken or the written text, it's all based on the sequence, and we are dealing with sequence. So we can definitely play around the probability, but we have certain things in our hand. We don't have certain things coming up. What we can do is that like we can predict. So be it a pronunciation phoneme or be it a be it a text. So here we are understanding what can be there. So that's what I was telling here. So yeah. So even though you don't have this window pane, even though you don't have this is a, okay. I'm sorry, I wrote this here. Okay, should not have written good prose like. So this is what our pronunciation model gave. Then the is a window pane will all be filled by a language model. So that is the moral of the story. Okay. So, but how they are actually doing? Again, they are playing around with the probability. So, language model is tasked for predicting what comes. The students open their books, laptops. Like, what is the probability? So, this is how the probability. This is a conditional probability you can think of, given x2, xt, x1. to xt. Okay, so this is x1 and this is x2, x3, x4. Okay, so here t is equal to 4, and given these words, what is the next word? So t plus 1 is going to be books, laptops, exams, and mind. So if you look at it, the students can open their book, can open their laptop, can they won't open their exam, they will only write their exam, I think. Yeah. And yeah, they can open their mind, but rarely it happens, no? Right, so it has to be one among this. Number two, everything are close. So book, laptops, they're all very close. So what is the most probability? So that is what is given by the language model. It's basically it's also Markov model, inspired from Markov model, Markov property, and based in probabilities. So this you would have seen in
Recording in
text.
progress.
They don't work on speech, and these are speech. So we don't need to break our heads too much. So these are pre-trained models, and they are trained with millions and millions of words. So this is by Google. BERT is by Google, and there are so many variants of it. You just go to you can just I think many of you know how to use BERT. So
Recording in progress.
Tech. So this is a PDF of the research paper from Facebook AI. So now it is Meta AI. So you can have a look. I'll share this PPT after this talk. So this you can this paper you can read. So this is the wave to wake model. Wave to wake model is nothing but the pre-trained model. So how it understands. So we don't need the wave to wake models are pre-trained models as in they've already been trained with a huge amount of hours of data. Okay. So the ideology behind these pre-trained models is that when we the ASR system that we were building so far, they were language specific. So if you had built it for Malayalam, then it will only work for Malayalam. It cannot work for the other languages. But the beauty of all these wave to wave these pre-trained models is that so they deal with multiple language speech representation, that is cross-lingual speech representations. That's what they deal with. What the beauty is that like when you have cross-lingual embeddings, no, so you're forcing all the language embeddings in a single thing, a single place, and you're training. What happens is that some languages are high resourced. When you speak of English, they have a huge amount of data, but that facility of that question is not available for many low resource languages. So we have to create data. So that itself is a cumbersome task, right? So you can't sit and create the data, but after creating the data, you don't even know like whether it will work out or not. It's after taking so much of pain. So high resource or medium resource or lowest resource languages, they're all put together. And this cross-lingual speech representation. So I mean, though it is a low resource languages, so they are able to, there's a mapping from one language to another. So that is cross-lingual speech embedding. So that is helping to even understand the low resource input. So this is XLSR. So you can, I'll just give the link. You can just try XLSR link, it will come. So, but there's a bug, so I couldn't just bring it here. So there's so many blog and there's so many YouTube videos spoken by the Facebook people itself. So I would suggest to listen to the videos or the blogs written by the Facebook people itself. So they are better to understand. That's what my personal experience. So multilingual wave to wake is a single. So 128 languages is able to handle now. So it's you don't need to train anything. So all you need to, so maybe like, for instance, I was talking about this dialectal identification. Or maybe they would not have handled that dialectal thing. So we can fine tune it. So but a small amount of data is sufficient. So you have a large amount of data already pre-trained, but whatever downstream task as in, these downstream tasks as in, like, for instance, I want to recognize a dialectal system, then the dialectal thing is not handled by the pre-trained data. Then I can top up the training data using this model. I mean, using on top of this already trained data, and I can use it for my own purpose. So that becomes a research. And translation, speech to speech translation. So we can even translate from one language pair to another language pair, which has not been done so far. Classification, yes. These three things are very popular in speech. Either you can recognition is like basically understanding what has been spoken. So that is ASR, converting into text. Translation is like you're understanding one language to another. So either speech to speech or speech to text or whatever form we want. Classification. There's so much to classify in the speech. No? So when a speech is spoken, like whether it is like we classify text into the movie reviews, or we categorize the movie based on romantic or comedy movie or something like that. What kind of emotion is being exhibited? So we can also do the same in a speech. For instance, like recently, hope speech and hate speech detection has been becoming popular. So like whether the somebody has posted something, and we want to understand like whether it is a hate speech, is it targeting a particular group? So is it worth to be on the internet or something like that? You can classify, you can identify classes, a number of classes, and you can do it. So what I'm trying to tell is that like you have a pre-trained model ready, you can do it for this a downstream task. So all you have to do is that like if you want, you can fine tune it and top up with your own data, and you can play around and build models. Okay, so this is what I got from their blog, to just give you an understanding of like how these pre-trained model work. Okay, so what how they work? They were simply they had put a very neat video. So maybe I'll post all the links. So speech input is given, and a generative adversarial network is there. Okay, so this two things together is represented here. Okay, so this speech input is working on the generator. So generative adversarial network will generate the text. No? So it's like RNNs. So it generates a text. So how are you? This is how are you. This is how are you. It is actually predicting. It is absurd, right? Then what we will have a discriminator. So discriminator will only discriminate whether it is a real thing or a fake thing. So whether it is existing in the language or not. It is human spoken. No, it just classifies as fake. And then the diagram goes this way. Okay, so discriminator, and they also complement with the real text. So this is a spoken text, and this is the real text. She likes tea. Then that is given by the discriminator. Then it just tags that real. So real and fake. It has the job of the discriminator is to understand whether it is real or fake. Yeah. So now what happens is that the feedback of the discriminator is continuously fed to the generator, and it tries to improve. That's what the core of all the deep learning mechanisms, right? The feedback. So it keeps understanding, and it tries to makes itself better and convert this Tavario into Havari. So that's how these wave to vec models are actually going. So it's self-supervised. So we don't have any data there. So we are just giving the data, and it is self-taught. Okay, so we will see some codes. Yeah. So far, any doubts?
No, ma'am.
I'll post these links in chat box. What I would suggest is that please take a copy. I've already tested it. Uh, just go to file. You all got the link.
Yes, ma'am.
Okay. So you can go to save a copy in Drive. Just click it, you'll get a copy. I'll also do that for you. So you get a copy, then you can own it. So you can keep it for yourself. Okay. Ready? Shall we see?
Yes, ma'am.
Okay. This is a transformer. So I'll just show you. This is Hugging Face. So you all can have a look at it. And the people who are working in image processing also, they have pre-trained image. I think it's VIT, visual transformers is there. So you can models, just go to models. So if you look at it, there is n number of models. I was talking about this robota and all that, right? You see this robota, Twitter robota. So many people are coming with their own bird or robota. So you can check these models. You can search for them like for image, speech, and text. As far as I know, so there are zero shot models and pre-trained models available. So you can have a look at it. Fine. So this is transformers. So the transformers, so you can also read what are transformers. The transformers are the ones um, um, introduced by Google. So you can have that paper also, transformers. You can read that. Attention is all you need. Searching for an, yeah. So this paper is actually a good paper. So attention is all you need. That's when they came up with this concept of transformers. They first introduced for text, and then now it is being, and this is first developed by Google, and then later Facebook took this, and they said we'll make it better than this. And they also got inspired. Facebook also got inspired from this transformer, and they built the robot art. So you can have a look at this. So that transformer is the core. Okay, so that's why I wanted to tell is that like this transformer we have to install. So inside the transformer there are so many modules. This is the core. Okay, so this version, normally we don't bother about the version for this wave to wake. This version was required. So you can run it and see along with me. It was already tested. Uh, Yes, and you have Torch. So this is a deep learning thing. So you can install this. It'll take few seconds, so but it'll get done. So yeah, everybody. I'm sorry, I did not ask this. Like everybody are familiar with Google Colab, right? For those, meanwhile it is running. So for those who are not, I think many everybody should be familiar. But still, I would say this: just go to Google, just press Google Colab. You'll get this. And the only thing is that like you should be pinned up with some account, Google account. I use this. So you go to file, you just type new notebook. That's it. So it's a cloud-based provided by Google, and yeah, so you can name it. So it's INV is Python notebook. So I generally use this. I don't use I mean standalone because it occupies a lot of memory in my machine. So I prefer to use Google Colab. So this is Google Colab in case. All right. I think it should have done. Fine. So got over. Fine. So oh yeah, so this Librosa is meant for processing the speech. So that's a Python library. And from transformers, we install transformer, right? The transformer is a core mechanism where it accommodates all these pre-trained models. But we are only bothered about these two models. Okay, so that is wave to vec for CTC and wave tokenizer. So we are importing them. Okay. You can, you want me to send this, you can use some .wav file. Do you have it in your desktop? So you can just quickly record some voice and save it in .wav format. I'll just take my, how do I send it? I have my own voice. Is there any way of passing this? Or you have your favor? Just to have you can open your recorder. I'll give you some, we'll spend some time and you save it in .wav format, and that wave file, you will upload it. Just click arrow and you can upload that file. It will get uploaded. So I'm copy pasting that content here. I'll wait for a while so you can record some voice.
Okay, ma'am.
Done. Saved as .wav file. Yes, done. Shall we go ahead?
Yes, ma'am.
Okay. Yeah. So when you just play it, it'll. Hello. Welcome to Python programming. Okay. So you can also test. Can anybody play that for me? I'll feel better. Unmute and you can play what you have. Anyone? Okay. So we are loading that text file. I don't know what happened. Yeah. So this is the rate. Okay. And now this is the important part. So this is how we load that pre-training model. And so tokenizer, we are loading the model. So wave to vec. For this also, there's a paper. So I think I've given the description in the slides. So you can read the paper like in depth of how this wave to vec. So we are passing the audio to the tokenizer of this model, and but it's not accurate. That's what I understood. Okay, and it'll predict it. Now we are going to do the transcription straight away. There's no, if you look at it, there's no feature extraction. We just gave the input. We've loaded the model, and now we are going to transcribe it. So we are decoding it. We had the model and we are decoding it. This is what it is printing. I said welcome to Python programming. I don't know. It is not able to understand this Python programming. So it is understanding is Dentro programming, Dentogramming. Maybe this has to be fine tuned. Maybe did not understand, or I have to speak it properly. I don't know. Can anyone tell me like what input you got and was there accuracy? There's no accuracy so far. We have to fine tune it because we are working on it, and this model has been released recently, and it needs a lot of fine tuning. Anybody test it? Okay. If somebody wants to share. Okay, fine. Okay. This is what I wanted to say. And this wave to wave model, you can have a look at it, and you can fine tune it for your own needs. Okay, so this was one, and we'll go to the next thing. I'll pass it on. So this is by Google. We're going to do a speech to text and text to speech. So that also you can open it and save a copy. Yeah, so this is speech recognition library. So that was Librosa, and just have a look at the libraries that we are using. So this is by Google. This is pretty accurate. They have used deep learning models at the back end, and this is pretty much easier to understand. But only thing is that like the difference. This is accurate. I don't deny. But the only thing is that like the advantage of that Facebook model, though it's not accurate, but you can use it for your research purposes. So if at all you want to do a speech recognition, then you can use that pre-trained model and you can fine tune it. But we cannot do that here. So you it's a black box. You give input and give get output. So maybe you can use this API, this library for some other purpose. You're not bothered about speech recognition, but you want to convert a speech to text or text to speech. This is the best way of doing it. Okay, so what we are now going to do is that we are going to install this PyTTS, that is text to speech. We are going to give text and then it is converted into speech. So we are installing Pi Audio. So these are the libraries which are I don't know, it is not installing. Okay, fine. So now what I'm going to do is that I'm going to upload my sample again. Okay, I think now it will work. I gave the file and you can see hello, welcome to Python programming. Now you see the difference. So this is using the recognizer Google. If you look at a close, have a close look at it, you can change this language code and you can you can change the language code and play around accordingly for the rest of the language. I think for Malayalam it is enabled. So we are also going to see that. So this recognizer Google, so this function is actually doing this job. But this actually I had said hello, welcome to Python programming, but this is able to do that job. So this is text to speech, speech to text. Okay, but here now we are going to see about the text to speech. This is also fun, and that is GTTS, that is Google Text to Speech. So again, we are installing all this. Okay. This is English. So you save it in sample.mp3. I'm giving this English sentence and language code as EN, and the save mp3 will soon come here. It's not appeared so far, but it will take time. It will come here. Yeah, it has come. So this, when you play it, no, 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 no. It has to.
ഇന്ന് ഒരു നല്ല ദിവസമാണ്.
No, no, I'm sorry. I think I'm playing the wrong. It should come it as I like NLP. No, I'll just say change the file name.
I like NLP.
Yeah. So did you all hear that? Yes. And so we can also give some Malayalam. I do not know Malayalam, but I will try to translate it. And That's what I had tried. So we can take Malayalam. Is this right?
Yes, ma'am.
You should understand. Okay, fine. Where are we? Okay. This one. Okay. So instead of this Hindi, I will give Malayalam, and then we'll change the language code ML. And save it. It works for all Indian languages, most of the Indian languages. You can try for which language.
I like NLP.
No, this I think I'm playing the wrong thing.
I like NLP.
Something has gone wrong. 1 second. TTS2. Very good. I'm sorry. I'll delete this.
ഇന്ന് ഒരു നല്ല ദിവസമാണ്.
Yeah. So this is uh, text to speech and speech to text. So you can play around with all the languages what you know. And yeah, finally, this I'm not going to run because, but I'll just show you because uh, you can even do a speech to speech translation. So given, because translation is there, right? Like this Google Translate function is there. So you can also incorporate that and speech to text, give the text to translation, and then convert that text to speech again. So it becomes a speech to speech translation. Hope you all got it. So that I'm leaving it as a homework you can do. So this is finally, so we were talking about three downstream tasks, no? So about speech. So we have three things we can do. So either we can recognize, that is given a speech, it is converted into text, that we have seen. And speech to speech translation, that I told you, right? Like you have a speech to text and text to speech. You make a combo and using the Google translation. So you can even Google translation, Python code, if you put it, you'll get the, it's just a function. That's it. This API you can use. Google Trans dot languages. You import the translator, and this translate. So you give the translate. You give the appropriate language codes. I think you will get it. It's only a few lines of code. So that I'm leaving it to you. So what I'm trying to tell you is that we have recognized. So we have even translate. We can even translate that. I'm giving it as an homework. Now, finally, I said we can also classify. So one such example I'm giving. So when you look at this, so this is a classification. It's emotion detection. So this I got from, I think I got from Kaggle. So you can even take a copy, but I'm not taking, I'm not going to run it because it will take a huge amount of time. I'm not going to run this. I'll just tell you. This is taken from this. I'm passing on the link from where I got this data set. So this is Toronto speech data set. So this is a very huge data set. You can download it and you can make use of it. That will take a lot of time, but I've already run it and kept it for you so that I can just we all can have a walkthrough of what's going on. If you look at it, so we are using pandas and Zbon. So these are all libraries. Interactive Python, Librosa are the main libraries here. If you look at it, and I've imported the test Toronto emotional speech data set. So that speech data set is very huge, and so we are going to classify what emotion is present. I think there are 5 to 6 emotions. So we are going to classify, given a speech, what is the emotion of the speech. Is the speaker happy? The speaker is not happy. So that's what is the goal. So these are the first 5 labels. So these are not the whole labels. So I'll show you what are the emotions. Yeah, this is the emotions: angry, disgust, fear, happy, neutral, and sad. So these are all analysis of the data. So the various ways of I'll just play it for you. Okay, so what is that emotion? So for fear, this one sample they have given. This code works, so you can just run. All you have to do is that, like, why I'm skipping this part is that because the data set loading takes a lot of time, so I don't want to waste time. So you can just download the data set. I've given the link. I think I posted the link also. So you can download the data set and you can import it and you can run this code. So this code works. So for each and everything they have given, and this is the MFCC I was talking about. So this thing was not there in the what do you say, that pre-trained thing. So they did not do a feature extraction and all, because you have a pre-trained model and everything is going on there. But here we extract the features. Okay, because we are using a neural network here. So that is also one of the reason, like, why I took this code. So in this code, what we are actually doing is that we are extracting the features using MFCC coefficients, and we are passing to a neural network. This will be skipped when you use the pre-trained model like XLSR or Wave to Beck. Okay, so this is how I was telling you that the speech will be included as a vector. No, so this is the vector I was talking about. Okay. That's when, like, we cut into 25 milliseconds, like each and every frame, like what is in there, that's what it is showing up there. And so sklearn library, we use it for machine learning models. So you can see it here. I told you, right, the LSTM famously it's a flavor of RNN, long short-term memory. So we are using that network, and we are using it as a classification framework. So this is the framework. Yeah, this is a training thing. What was the accuracy that is last reported at the end of the epoch? Let me see. So it's around 98 or 99. And so the graph is plotted for the accuracy. So you can check this. I'm leaving this to you. So, and the link for this code also, code and the data set I've posted. So here I stop. We're open to ask questions. Did I post this link? If not, I'll do that again.
Okay.
Yeah, it's there.
Thank you, ma'am.
Uh,
Participants, you can post your queries in the chat box. Ma'am,
yes, ma'am.
We can use this BERT and Roberta model like this for text processing, right?
Yes, ma'am. BERT and Roberta models, they are also meant for classification. Classification it can do. I don't think Roberta and BERT models can be used for translation. For translation, we normally use generation, I think TA. One second, give me some time. Marion MT. For translation, there's one more model called Marion MT that you can use. So normally, this BERT and Roberta models are famous for classification tasks, but
Okay.
that's for text, ma'am.
For converting Malayalam text to vector,
Mm.
uh, is BERT is useful for us?
Yes, ma'am. Of course, yes. BERT actually converts the words into vectors, embeddings. 788, 786 is the dimension of the embeddings, I guess. So yeah, it is pretty much good. You don't even need to do a classification. If you are meant for doing some other task, but you want the embeddings to do that, you can pretty well use BERT. You can use mbert or you can use Roberta. It works for Malayalam.
Okay. Thank you, ma'am.
Well,
Participants, if you have any queries, you can ask. I think no more queries, ma'am.
fine, ma'am. That's fine.
Okay. Thank you, ma'am.
Welcome,
Um,
ma'am. Pleasure is mine.
uh, so, thank you, Dr. Subalalitha, ma'am. That was an enlightening and insightful presentation on speech processing. She explained about the work automatic speech recognition and how the features are extracted from speech signals. And she also delivered different language models like BERT, Roberta, and also vector conversion tool used for speech processing like wave to vector, etc. She very well demonstrated a sample code of text to speech and speech to text conversion. I thank you from the bottom of my heart for taking time from your busy schedule. Uh, Please accept a token of gratitude with our sincere thanks, ma'am. I'll share the screen. Thank you, ma'am.
Thank you so much, ma'am. I'll take a snap of this.
Yeah, sure.
One second. Thank you so much, ma'am, for this.
Thank
Uh,
you, ma'am.
Thank you so much for the opportunity given. It was a great morning talking to you all. Thank you, everyone.
Okay, thank you.
Thank you.
Okay, participants, I'll share the. Okay. Uh, Sorry. Okay. Participants, I'll share the feedback link in the chat box. Please fill the form. Next session will be start at 1:30. Uh, Please fill the feedback form.
Recording stopped.
Okay, thank you, participants. We'll start the next session at 1:30. So we are going to wind up the session. Thank you all.